Okay, today I wanted to tell about the other gain functions. So far we computed the gain function for a 1 plus 1 wave equation. So we know that a solution of this wave equation with delta functional right hand side, delta of x. Well, let me call it g of x of tx t0x0. So with delta function on right hand side, and with initial conditions that this g of tx 0x0 is equal to 0. G and its time derivative, it's also 0 for t equals to 0. So we know how to solve this equation, and the answer for this is g of t 0x0. So it depends only on difference. So it is theta of t minus t0 1 half theta of x minus t well, let me write it as a function of let me put this variables equal to 0 because it is a function of difference in any case, and but it is complicated to write it as a function of four arguments. So it is just theta of t, theta of x minus t minus theta of x plus t. Something like this, and solution of this wave equation with some right hand side t minus uxx equals to f, and solution is written like u of t and x is a gain function, so is integral from minus infinity to t, or from 0 to t, integral from minus t to from x minus t to x plus t, so d t from no, not plus t, but t minus t prime minus t minus t prime dt prime dy f of t prime y. So this is the application of this formula for the gain function. So for generic gain function, it is u of tx equals to the integral from minus to plus infinity d t prime and dy, some gain function of t minus t prime x minus y f of t prime y, so something like this. And for this particular gain function, it is this integral. Right. So this was 1 plus 1 wave equation. So let us solve the same problem for the heat equation. We can do this already in d dimensions. So ut minus Laplacian of u equals to delta function of t delta function of x, which is a product of delta functions over all coordinates. Hmm? This with some right hand side f. Hmm? But it's the same solution. We just substitute. We just substitute the formula for this gain function, which we computed from the Fourier transform. Hmm? Hmm? Okay, so let us say that we are solving this equation for the gain function. So it's not the arbitrary u, but some gain function. And let us represent this gain function as the Fourier integral. So g of t and x, so literally as before, as for the wave equation. So this gain function is t dx over 2 pi to power d plus 1 e to minus I omega t plus I kx. Some g tilde of omega k. And and if you want to write the Fourier transform for the delta function, so what will we have? Yes, thank you. Omega and k. And what is the Fourier transformation of delta function of t, delta function of x? So in the same integral, so what should I put here? Hmm? Why? Hmm? So the question is, what is the integral d omega e to minus I omega t? It is correct, but with what precise coefficient? So it's almost delta of t, because you remember that one of the Fourier transforms is a direct or inverse. Usually it is that one that contains integrals in omega and k. It should contain 2 pi, and so if you integrate a delta of t with the exponential, it gives 1. So in the so it's inverse transform of 1. Hmm. So. Uh, yes, or we can divide by 2 pi in this way. So, who should be written there? Mm. Mhm. Hmm? No, but it is already there. If we, so, oh, the answer is that it is 1. And if you integrate, if you compute this integral, we will get 2 pi to the power delta to power delta plus 1, which will precisely cancel with this 2 pi in the denominator. So, is it clear? By the way, there were 2 lectures the last week, and I told some details about how to define such kind of equations rigorously, like how to write it in the weak form, and to give some rigorous meaning to this. So if you wish, you can watch them, but it is so as you see, it is not necessary to be able to solve such equations. So just to fill in possible gaps. Uh, okay, but if we have this, we can just take Fourier transform of that equation, and as usual, find that. Uh, uh, so we can find the formula for the Fourier transform of this gain function. So, and what will be this formula? So, what is g tilde? So, who can tell this? Uh, what do you mean? We just substitute this g and deltas as and therefore transforms into this equation, and then find g tilde. Oh, but the first question, what happens if we take this Fourier transform and act here with dt minus Laplacian? Or what happens on the right hand side? Hmm? So, but what do you mean by ordinary? Hmm. In what variable? Oh, so there is this Fourier transform for g of t index. It was written like this. What happens when we act with this operator dt minus Laplacian on the right hand side? How does it modify this expression? Hmm? So the Fourier transform of g and of t and x is given by this formula. What is the Fourier transform of dt minus Laplacian of g? Hmm. Yes. Hmm. Yes. Hmm. 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 uh, just IK. uh, Oh, but it's not a number. It's this triangle, so it's Laplacian. It is a sum of d over d dx dx1 squared plus and so on plus d 2 in dx d squared. So what? Hmm? So what will it be? Hmm? Hmm? Mm-hmm. Yes. So it is this. And now we say that Fourier transform of a sum of that Fourier transform of this should equal to this. So this equals to this, and therefore this again function is I over omega uh, mm, minus I k squared. Right? If I don't miss in the sign, well, yeah, it should be like this. So, are there any questions about this? So, so we can say that this operator acts diagonally on uh, in this basis of Fourier modes, so we can invert just by dividing by corresponding function. And hmm, so hmm, because our equation is saying that this equals to this, So their Fourier transforms should also coincide. Hmm? So, and then we just solve this equation. So, so is it okay? So and this is a similar kind of argument that we used for the wave equation. In that case, the difference was that it was the second derivative in t, and it had omega squared minus k squared, and we had this problem with poles on the real line. But now we don't have this problem because ik squared is purely imaginary. And we will find the Fourier transform quite easily. So namely, uh, uh, we now remember this definition g of t and x equals to the integral from minus infinity to plus infinity in all variables. Uh, I e to minus I omega t plus ikx over omega minus ik squared. The omega dk over 2 pi to d plus 1. So in the first integral to compute in the integral in omega. So so again, we can draw a picture that corresponds to this integral, maybe two pictures. For t greater than 0 and for t less than 0. So it is omega plane, and there is this pole of expression under the integral ik squared. And oh, let me think. Probably. So sorry, I made some mistake because it was minus Laplacian. So here it should be minus I omega plus k squared. Because I was starting to think that we get some wrong sign in the answer. Uh, so this pole is here, minus ik squared. Okay, so originally we have integral over the real line, but now we can use this trick by completing this integral by a semicircle going to infinity. And the question is, in which of these pictures we can draw this semicircle in the upper half plane and in which in the lower half plane. Hmm? Hmm? Uh, like this, right? And because this exponential goes to 0 when t is positive, and I goes to minus infinity. And here, especially, we can close it in the upper half plane. So this integral is automatically 0 because this function is analytic in the upper half plane. And here we need to compute the residue. So we write theta heaviside of t because so it's for t less than 0. And here we just need to compute this residue. So uh, so the integral in k stays the same, in k over 2 pi power d. Um, and who can tell what is the answer for this omega integral? So I will write the part which depends on k, that originally depends on k, ikx, and what do we get from this omega integral? Hmm? What? Hmm? So hmm? so mhm. And so, mm, and no, why? How? It is just first order pole in omega around point I case. So you take the factor which multiplied this pole and substitute omega equals to minus ik. So since it is minus ik squared, since it is minus ik squared, it gives minus k squared t here. And you also multiply by the factor 2 pi I, which is the integral dz over z. So it gives 2 pi I. And it divides original 2 pi, which was in the Fourier transform. And it is also multiplied by minus I, because there was a I factor in this integral, and we also integrate clockwise, not counterclockwise. So there is also this factor, and all these factors together cancel. But in general, yeah, the leading contribution is this one, e2 minus k squared t. So, and we already. So, are there any questions about this? And in principle, we computed this kind of integral, but probably it was one-dimensional, but it is the same. So to compute such a Gaussian integral with quadratic k and with linear, with something linear and k, we should collect full square and then shift the variable. So it will be the integral dk over 2 pi to the power d e to the minus t. So we write the first correction so that it reproduces this linear term by writing I over 2t x. So we have this, and then we have term which should compensate the last part of this full square. So it will be k squared over 40. So are there questions about this? Hmm? Who? Where? Minus t times the square of this. So I just wrote something that reproduces ikx when we start expanding it in powers of k. And the last term should be compensated manually. So, hmm? Yeah. Ah, yes, yes, thank you. Yes, yes, it is this one that comes from the last part. Thanks. So, and now we can use, so, any other questions? And now we can use the fact that this function goes to zero when any component k goes to zero. So in principle, it was some integral in the complex plane over some shifted contour. But we can say that this contour can be sent to zero at infinity, and then we just move it to the real line everywhere else. There are no singularities, and it can be done just for free. So, so we can write that this integral is theta side of t times this integral dk over 2 pi power d e to minus t k squared minus x squared over 40. I've just shifted all components of k by that imaginary number. And so who knows how to compute this integral? Hmm? Hmm? Yes, because the value of this function at infinity goes to zero, like e2 minus x squared. So this integration contour can be deformed first at infinity, and then since we deformed it at infinity without changing anything, we can deform it continuously in all other points. So it can be done only if only in the situations where we don't move the contour in the domains where the function is big. For example, if it was some integral from between some finite points, we would not be able to change its endpoints. And also, this function should be analytic. We should not emit any poles or branch cuts, because if we emit some pole, we should write a contribution of this pole explicitly. Mm. But here it is just exponential. It doesn't have singularities. So, mm. Okay, but how to compute on this integral? For example, there are preliminary questions uh, about this integral. So, who knows? Just this. Mm. Mhm. Where? Mm. Yes, because we can just scale x by square root of alpha. This becomes this integral, but we also scale in integration measure, which gives square root of alpha in the denominator. Yes. So what we'll get in this case? So this one was there initially, and uh, to what power? Hmm. Yes, and because we have d such integrals for each component of k. Yes, but we are solving the dimensional problem. So hmm? Yes, it was always there. Thanks. Yes. Mm. Yes. Thanks. So it is. It stays there, and it's kind of the essential part of this gain function. So the final answer is uh, heaviside theta of t over 2 over 4 pi t to power d over 2 e2 minus x squared over 4t. So if you have our heat equation with some right hand side, so mm, so let us write, well, so it equals to some f of t and x, and there is an initial condition for this u. We say that u of 0 and x equals to 0. So then a solution is given by u of t and x. I wrote one-dimensional, but it works for arbitrary dimensions. Laplacian of u, t and x. So it will be the integral from 0 to t. Integral from integral over rd. So in dt prime, dx prime. F of t prime x prime over 4 pi t minus t prime power d over 2 e2 minus x minus x prime squared over 4 t minus t prime. Oh. Are there any questions about this? So I just substituted the definition of the Lagrange function, and this terminated this integration domain in t at in t prime at time t, because other part of this integral will involve some values in the future. So far we know this function, but we can ask a different question. When we solved, for example, the wave equation, we started from some initial value problem where we fixed u and its time derivative at t equals to 0, and then solved this equation without the right hand side. But I want to say that actually one Lagrange function can be obtained from another one, because so it can be done in such kind of physical way. We say that if we put some delta source in the right hand side, it creates some delta-like initial condition for u, and then we can solve this equation with 0 right hand side. So it suggests that the Lagrange function should be the same. But this can be derived in a kind of more rigorous way, and we can also give some answer also for the problem with boundary conditions. So, namely, let us suppose that we know how to solve this problem. And let us suppose that we manage somehow to compute this gain function on some domain, for example, not on the whole space, but for example, on some interval. Uh, So suppose that we are solving the following problem. So again, u t minus u, so let it be one dimension, minus uxx equals to 0, and mm, domain we are studying is from 0 to 1, for example, or from well, from A to B. T is from 0 to infinity. And we have some boundary conditions that, for example, u of t and a equals to 0, and ux of t and b equals also to 0. We can impose such different boundary conditions. And there is also initial condition that u of 0 and x equals to 0. So there is such a problem. So we can draw some picture. So it is x. So this is x. This is t, and we have one boundary condition at a, saying that u is 0. It is some kind of a fixed temperature boundary condition, because if we interpret this u as a temperature, this boundary condition will mean that there is something with very big heat, no, not heat conductivity. Oh, it's something very massive that does not change its temperature, so it always 0 at this boundary. And on the other boundary, sorry. Let us say that it is a problem. No, I don't want to make it 0. I want to make it some arbitrary function that depends on t. So f, so u a of so some f of t and some g of t. And here I want to put some arbitrary initial condition. Sorry, u0 of x. So there is this boundary condition. There is some temperature that depends on time, and there is some heat flow on the other side, which is so can denote it in some other way. So which is also some function of time. And there is some initial condition here at t equals to 0. So it is one problem. And let us suppose that we know solution to the other problem. So namely, it's a problem for the gain function. So we write exactly the same, like gt minus gxx equals, now it will be a product of delta functions, t minus t0, delta of x minus x0. So solution 2, and I'm writing the problem, this problem here. So this equation holds for x in this interval from a to b, and t from 0 to infinity. And since we want to separate a problem with the right-hand side and problem with non-trivial initial and boundary conditions, we ask this gain function to describe the problem with zero initial and boundary conditions. So, namely, u of g of t t0 x and x0 for t equals to for t equals to 0 equals to 0, g of t t0 x x0 for x equals to a equals to 0, and gx for t t0 x x0 for x equals to b equals to 0, like this. So this way we separate the two problems. So uh, are there any questions about the formulation, or is it fine? So and now the main trick, which is used here and in all such relations between different gain functions. So suppose that we have that we managed to solve this problem somehow, and suppose that we know this gain function. So this gain function is something that we need to have. And now let us compute the following integral. So let us take this equation g t minus g x x uh, let us multiply it by u of t and x. So we know that it equals to delta of t minus t0, delta of x minus x0. And here we also multiply by u of t and x. So this is satisfied because it is just satisfied by the gain function. And now let us integrate it in dt and dx. So let me write this integral separately from minus infinity to plus infinity dt, from minus from a to, well, maybe from 0 to infinity in dt, from a to b in dx. And here the same, from 0 to infinity in dt, from a to b in dx, right? So the right hand side mm, So actually there is one thing uh, uh, which I don't like. Mm, Ah, yes, I forgot to do one important thing. We actually need to consider this kind function. Well, so let's write here integral from minus infinity to plus infinity. We need to write a grand function of a negative time here, uh, uh, or uh, better to say of t0 and t. So we need to write a grand function. Uh, 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 so it is this difference for the heat equation. So this tilde of t uh, t0 uh, x x0. It is actually well, tilde is a bad notation. Let's call it g hat. It should be a grand function of, so it is grand function of t minus t0, x and x0, and it should be a grand, so this g hat. This grand function should be a grand function of t0 minus t, x, x0. So, uh, so this g hat satisfies this equation with opposite sign of derivative. So dt minus dt g hat plus minus g minus dx squared g hat equals to delta of t minus t0 delta of x minus x0. So sorry. So here we should change on this sign. Uh, no, y minus g. And because original green function solved this equation, and here we just changed the order of t minus t0. So time derivative of this differential is minus derivative in the first argument of this function. So it solves the different equation. Yes. Okay, okay, okay. So what I want to do now, I want, of course, to integrate this right-hand side, and it will give us u of t0 x0, and on the left-hand side, we need to integrate this by parts. Uh, so, mm, no, so the integral is from 0 to plus infinity. Uh, and we are integrating by parts. So the first integral is the integral from uh, so the first term which we write is the integral. It's g hat times u minus g hat times u computed uh, in the limits from 0 to plus infinity. And it is still integrated in dx. Maybe let me write it like this. So the integral in dx stays. So integral from a to b in dx stays. And under the integral we have minus g hat t g hat times u from 0 to plus infinity. Plus the integral from 0 to plus infinity u t times d hat dt minus this original integral from 0 to from a to c from a to b g hat x d times u dx, and all this equals to this, right? And now let us compute this change from 0 to plus infinity. This grand function at plus infinity. So this grand function is g of t0 minus t. And when we send t to plus infinity, it just vanishes because it vanishes for negative times. And also because you can go to 0 there. So the only remaining term is on the lower boundary, and this is g of t0, x and x0. So integral from a to b dx g of t0 x x0 times u of u of x, u of 0x. So is this fine for the first term? Now there is this, there is also the second term from a to b, u t j hat dt dx, and also the integral in dt. And here minus this integral also so I wrote integral in x there, so this integral should be in t. So we have the integral from 0 to infinity in dt, and here there is this integral in dx which we want to integrate by parts, and we want to integrate it by parts twice. So the first integration by parts gives g x hat u from a to b. The second integration. So what will get what will give the second integration by parts? So which term will we get if we integrate this function by parts? But no, it is a kind of well. Let us do it step by step, actually. But I wanted to say that we can do the second integration by parts immediately. But well, let us write it first. So it will be integral from a to b, g hat x ux dx. So and this all equals to u of t0 x0. Uh, yeah, like this. Well, let me write on the same terms. Actually, I don't need to write vectors for x because it's one-dimensional. So it's g at x u from a to b. Uh, so now we integrated by parts again, and now this. So what will be the second contribution from this integral? Hmm? Uh, no, no. Be careful. I decided to consider mixed boundary conditions in a sense that on one boundary g is zero, and on the other boundary gx is zero. So we will still have something. So. No, valued in A because a G is equal to 0 there and Gx is equal to 0 at the other boundary. But it's the next question, and the previous question is how to write another term. Like what happens when we integrate this by parts one more time? Uh, so our goal is to move both of these derivatives to u because we know the equation satisfied by u, and we want to translate this equation for g to equation for u. Hmm? Hmm? So what? Hmm? No, the integral in the last part. Okay, but what kind of integral would be? With what sign? Mhm. Yes. And no, because how do you compute this? We say that it is derivative of that it is one function, it is another function. So here we have a derivative of function g hat times ux, and then we have g hat times the derivative of ux. So it will be g hat times ux from a to b, right? So it equals to u of t0 x0. But now look carefully at these terms. So we see that this term is well. So these two terms just mm, oh, wait, did they? Yes, and there is overall minus here. So these two terms together give us this heat equation satisfied by u. So we finally obtain this. So these two are zero. And we are left with just these terms, which can be now computed. All of them can be computed. So. So this integral from a to b g of dx g of t 0 x 0 so let us now remember who this u of 0x is. It is our initial condition. It is u0 of x times u0 of x. Then, so this term vanishes. Now let us look at this term. So g of gx of p is 0. So the upper limit does not give any contribution. And the lower limit gives a contribution like gx of g hat x. So so it will be g of t 0 minus t gx of computed at a. X 0. No, because yes, thank you. And u at this lower limit is f of t. So it is on this integral, and then this second integral, this second term now vanishes on the lower limit because g of x equals to a is 0. And the surviving term is on the upper limit, so it comes with the plus sign. So it will be plus integral of d t j g of t 0 minus t b x x0 times g of t integral from 0 to infinity. And this equals to u of t0 x0. So so we see that it is precisely the formula we wanted. Uh, on the right hand side we have a solution at arbitrary moment of time t0 and arbitrary point x0, and on the left hand side we have the integral with initial conditions. We have integrals with boundary conditions which go from actually from 0 to t0, because when t is greater than t0 this green function vanishes. And the kernels and the integrals are always the same. They are obtained from the same grand function of equation with the right-hand side. The only difference is that if this boundary condition correspond, if this boundary condition implied a vanishing of green function, we should write a derivative of this green function with plus or minus sign. And if it was some condition with a vanishing of derivative, it will be just this green function. So the point is that all green functions are either this single green function for the inhomogeneous equation or derivatives of it. And you see from this computation that it can be done for any equation. We can do this integration by parts in any situation. And also one may ask about the orders of arguments in the green function. It can be proved more or less in the same way, but in that case, we should substitute another green function instead of u. We can prove that g of t of t x 1 x2 or x0 is equal to a grand function of t x0 and x. So it's kind of exercise. Probably I'll formulate it more precisely, with the hints how to do this, and add to the list of problems. So it's actually, and we see that it works in this case of infinite space. And we can also write the analog of this formula, not the analog, but simplified version for the heat equation with initial conditions. So ut minus Laplacian of u equals to 0. X is in the whole space. T from 0 to plus infinity. U of t u of 0x equals to u0 of x. So we want to solve this problem. So who can tell the formula for u of t and x? So what is the solution of this equation? Hmm? Mhm. Yeah, and what should be instead of f of t and x? Oh. No, but I would say that it is some step back. Of course, we can solve this equation by switching to the Fourier image, solving this equation for the Fourier images, and then transforming back, and we will get the same answer. But at the moment, and you can do this, so of course. Is useful. Well, like if it is not absolutely obvious that you will get the same answer. But now I propose to use this a connection between different gain functions, which we already know. So because it's more universal. At least, what should it be structurally? Like, how many integrals will we have? So we have this initial conditions u0 of x, and we want to write a solution of this equation in terms of it. Hmm? In what variables? Hmm? Uh, who is plus first? Who is plus first? Like, what are the variables? Oh, yeah, RG. Why two? Hmm. But who depends on t? We have only one t, which is the time in which we compute the solution. So the picture is this: we have some plane with initial conditions. So there is it is t, it is so mm, it is d, it is rd. We have some, so it is t equals to 0. Uh, and we have some u0 of x. Or let us say that it is u0 of y at some point y. And we are looking for a solution at point t and x. So it is linear in u0 of y, in the sense that uh, a linear combination of initial conditions gives a linear combination of solutions. So it should be some a integral kernel uh, which uh, kind of sums the contributions from all points of this RD and gives the value of u of t and x at some moment t, right? So structurally, it looks like this. We integrate uh, in a point in the space of initial conditions. How to say it better? We integrate in the point of RD at t equals to 0 at the moment of time where we fix initial condition. This is 0 of x of y. So we have d dy. Then we have some green function that depends on a time and on this point x. T, x, y, u 0 of y. So this is this is the only expression that we can write structurally. So it is a kind of a generic linear transformation from the space of functions at time equals to 0 to space of functions at arbitrary time. So it is an integral kernel that depends on time. So the question is, what is this integral kernel? And the question is, what is this integral kernel? What should I write here? If I want to write this explicitly. Well, the answer is actually on the blackboard. So yes, but is it clear why that formula? Is it clear why that formula? So yes, but it was an again function for some equation with the right hand side, and we checked here, we derived that again function for non-trivial initial conditions is literally the same. So it is 1 over 4 pi t to power d over 2 e2 minus 1 over 4 t x minus y squared. Mm. And by the way, what can we say about this kind of function? What happens when we take the limit t equals to 0? Hmm? The limit of this function when t goes to 0. but it goes. Well, if you take arbitrary point, then it goes to 0, right? But if t equals to 0, so yes, yes, when x is different from y, right? Hmm. Yeah, it is true for x different from y. But what happens when t is equal to 0? Oh, when x is equal to y. This is 0. Eh, So it is, yes. So we saw something like this at some moment, right? So and let me summarize this. So on this. Mm, so this g of t x y when uh, when t goes to 0, uh, when x is different from y, uh, uh, it goes to 0. When x equals to y, it goes to infinity. Right? And we saw this for delta-like sequences. For some sequences of functions that approximate delta function. So we need to check just one thing. What is the integral of this function in the whole plane? Integral of dy of 1 over 4 pi t d over 2 e to minus 1 over 4t 4t x minus y squared. Hmm? Yes. So, uh, so this is precisely the definition of delta-like sequence. So we can say that the limit of because it is what? It is integral. It is this power of well, we can shift each variable to 0 because it is just shift of the integration variable, and all the integrals become the same. So it is this power of a single integral of the form 1 over 4 pi t square root 4 pi t e2 minus x squared over 4t y squared over 4t to power d. And this integral, so we have this formula which you can learn how to derive and so on. So this is 1 over square root of 4 pi t and this is square root of pi over 1 over 4 pi 1 over 4t. So it is 1. So is it clear? So we can kind of understand it this way. It is some function that is significantly non-zero on some domain approximately of size square root of t, because it is the characteristic value when this argument of the exponential becomes further 1. And this function is divided by square root of t to power d. Or we can say that we can rescale variables in this function. So it is something bell-shaped, quickly decaying at infinity with constant integral, but this is rescaled by a factor of t. So it is something of this kind. So and then finally it goes to delta function. This is like it's evolution of this function in the direction of decreasing t. So limit from for t goes to 0 of this grand function v of tx y is delta of a d-dimensional delta function of x minus y. So it's kind of product of delta of xi minus yi. Right? And this is what it should be uh, to guarantee that u of 0 and x actually coincides with initial condition u0 of x. Because this is literally what we are asking for. We are asking for solution which equals to u0 of x for t equals to 0. And this is precisely what happens. So this kernel becomes a delta function. So is it? Hmm? Yeah. Yes, of course. So hmm? Uh, so what's precisely the question? Well, in that case, t0 and x0 were just arbitrary points. We were looking for the gain function with delta function at t0 x0, right? So wasn't the question? So it's yes, it's value for arbitrary t0 x0, and this is what we are using here. So, mhm, mhm. so, mhm. so So we have this formula, and now I want to ask the following thing. Uh, uh, there is some transformation on the space of functions of this variable x in d-dimensional space. And now I want to ask what happens with the Fourier transformations of such functions. Namely, let us consider some partial Fourier transformation. I will use the same notation for it. So, namely, u tilde of t and x of t and x will be represented as the Fourier integral d k over 2 pi uh, 2 pi to the power d of e to the ikx uh, sorry, u of t and x equals to this integral of u tilde of t and x. Of t and k. So, and let us say that our initial condition u0 of x has the same Fourier representation. With some u0 tilde of k. The question is, what is the formula for u tilde of t and k in terms of u0 of k? So So there are different ways to understand this. You can substitute it into the equation and solve it, or you can look at this formula and notice that it is a convolution of the two functions. And then if you know that it is a convolution, you should know what happens with the Fourier images. So. You can try just to guess some answer and then we think if it is correct or not. Kind of some project for the answer. What can it be? Hmm? Mm-hmm. Well, let me write it, but then we will decide if it is needed or not. But where is x? So, no. So, oh, if you say that we should integrate something, then yes, but it's possible, but I want just some answer. Hmm? No, no, we don't have this. We have u zero of x, and we have u tilde zero of k. Who, but it is some bad notation. Well, let us call it x. But what's next? Hmm? I would call it k prime, to be honest, because it's not coordinate. It is a momentum. What gain function? This gain function is in the coordinate space, right? Mm. Uh, this gain function depends on coordinates. This should be the Fourier transform of a gain function, right? So uh, k g tilde of k prime. But here's this important point about this green function, that is a function of a difference of two variables. So if a green function depends on difference, then mm, what happens with the Fourier transform? So uh, let me maybe erase something. Mm, Maybe I can erase this. So suppose that we have formula like this: u of t and of tx equals to the integral in dy g of t x x y u 0 of y. Uh, and now say that u0 of y is the integral in dk k prime over 2 pi to power d uh, times u tilde of k prime e to I k prime y. And u of t and x will be u tilde of t and k will be the integral in dx e to minus I k x times this integral dd y. So I'm taking Fourier transform in x ddx. So this is Fourier transform in x of this u of t and x, which I substitute as this expression. d dy g of t x y. This is uh, this part. Oh, here it is. And then I substitute the formula for u0. So it is integral in d k prime over 2 pi to power d. U tilde of k prime e to the I k prime y. Mm. So, and what we are looking for? We are looking for the function of k and k prime that will pair with this utility of k prime. So we want to keep the integral in k prime first. So we write the integral d k prime u tilde of k prime. This is u0 tilde of k prime. This is what you want. And everything else will be some function of k and k prime. And let us write this function of k and k prime. So it will be the integral ddx d dy divided by 2 pi to power d. And this will be e to I k prime y minus I k x times times the green function of t, x, and y. Right? So this is what you call the G tilde of t, k and k prime. So this Fourier transform is kind of change of basis of functions from functions in coordinate space to functions in the momentum space. And this Fourier transformation is kind of a multiplication by a matrix that changes basis. And since this G is an operator acting between spaces, it transforms like t g times t inverse, like g tilde equals to g like t g times t inverse. So one is direct Fourier transform, another is inverse Fourier transform. So, but we just obtained this formula, and now let us compute this function. So we know that this gain function depends on difference. So G tilde of t k prime equals to this integral dx dy over 2 pi to power d e to I k prime y minus I k x times green function of t x minus y. So, and let us say that x minus y is some z. Let us denote it by z. No, how to add this? So x minus y. So we parameterize x equals y plus z. It is one variable, and another variable y is just y. So we do this change of variables. So this integral can be written as the integral d y d z over 2 pi to power d times. So now we need to change. We need to write x explicitly, and we will get I k prime minus k times y minus I k z. This and times g of t and z. So we see that two integrals are now independent. And so what do we get when we compute the integral in y? Hmm? Hmm? Yes, d-dimensional delta function of k minus k prime. And this will be something. It is just a Fourier transform of this function of single variable z. So it will be some g tilde of k. Hmm? Yes, I just no. If we write something like this, there is a single way to understand this. because of delta function of vector is a product of components of delta functions. So I just omitted this sign. So there are no other options. Okay, and the meaning of this formula is the following. We had something that depended only on x minus y, which means that it commuted with a translation operator. And since it commutes with translation operator, then it diagonalizes in the basis of eigenfunctions of this translation operator. And this is precisely what is written here. It is a diagonal matrix in the infinite dimensional space with diagonal values given by g tilde of k. So if we now use this knowledge here, what will we get? So how to compute this integral? Hmm? Mm-hmm. So, mm-hmm. And what else? Mm-hmm. Yeah. Mm-hmm. Yes. So just a multiplication. Uh, and so it's multiplication by the Fourier transform of this green function. Mm. But what is the Fourier transform of it? So what is the Fourier transform of this function? Actually, we should know it because we obtained it just as a result of computation of some other Fourier transform. So, no, what do you mean? It is a function of, it is some function of difference of x minus y, and we want to do this Fourier transform in this difference and get some function of k and t. So, but but do you remember? Mm, yeah. No, here, yes, we just derive this fact in some different way. But the question is, what is the value of this g tilde of k? What is the Fourier transform of this green function written here? Because in principle, we obtained this function as a result of computation of some Fourier integral. Uh, so So another way to think about this is to think about the differential equation which is satisfied by this partially Fourier transformed function. Because if we squeeze a little bit and insert here the differential operator, uh, so so u of t and x. So what happens if we insert here dt minus Laplacian? So u tilde of t and k. So what will work here if we insert here a plus n? Mm-hmm. Coefficient plus one, and what else? So so hmm? Yeah. Yeah. So we just don't touch anything else. So this t is just the same t. It is not in the exponential. So there is this simple operator. And if you say that it is zero that you satisfy the equation, we can just have a very simple ODE for the Fourier modes, right? And what is the solution of this ODE? So we want this to be zero, right? So what is the formula for u tilde of t and k? Hmm? So could you say it again? Oh, so the equation is f dot plus dtf plus cf equals to zero. So what, what function solve this? Hmm? Mm-hmm. Yes, and there, and it's defined up to a constant which should be fixed by initial conditions, right? And what is so it is a u0 tilde of k, because for t equals to zero it should be the original function. So here it is. So uh, and of course, so we obtained this function precisely by computing the Fourier transform of e2 minus tk squared. We could even obtain this easier if we start from this equation without this Fourier transformation in omega. And this is consistent also with this formula for convolutions and so on. And only one thing which I wanted to say about this is that so even if you start with some function which is not smooth, which is discontinuous, then any evolution in very short time already makes it infinitely differentiable, which is reflected by the fact that its Fourier components go to zero very, very fast. Even at a very small time. So it's kind of this Gaussian smoothing of a function. Okay, and that's all. By the way, the next time there will be two lectures on geometry. Wow. Okay, so thanks for this. Yes, so there should be geometry. So, do